All right, so in this video, we're going to be looking at how to simplify complex fractions. When we talk about complex fractions, we're talking about essentially fractions inside fractions. And generally, this is messy and difficult to work with, certainly difficult to enter into calculators and things like that if you want to calculate any values. So we want to be able to simplify them so that they're sort of normal fractions, normal rational expressions. Now, there are two methods for simplifying these. So we're going to look at both methods. They work fine, both of them. Sometimes one might be easier to work with than another, but sometimes it really doesn't make any difference. You're going to, assuming you haven't made any arithmetic mistakes, you'll get to the same place. When I was learning myself, I sometimes found trying to figure out which method to use was too much to kind of keep track of. And so I just did one way and it got me where I needed to go. And only after I felt more comfortable with the math did I feel like, okay, now I can like do it interchangeably. So that's fine. You want to get to the right answer. You want to simplify. And as long as you're getting to the right answer, you're good. So choose whichever method seems like it works best for you. So method one is basically simplify each part of the fraction separately. So create one term and then apply division. The middle bar, the big middle bar between the top fraction and the bottom fraction, it's just a division sign. That's all a fraction is. So this is a complicated expression that involves multiple divisions. And so you can just simplify each piece separately. And then once they're single fractions in the top and the bottom, then you can go ahead and apply division multiplied by the reciprocal and then proceed from there. Now, the second method, method two, is basically find a common denominator for all terms in the entire expression and multiply everything, again, top and bottom, so that you're multiplying by one, really. Anything divided by itself is one. So we'll multiply the top and the bottom by the same common denominator. By that common denominator. And what this will do will clear fractions. And so you're doing some of the simplifying sort of in position. So you don't ever actually get to converting this to a division problem. All right, so let's look at this from method one first. So for method one, we're first going to take each piece of the fraction. So 1 minus x over x plus 2. And what I'm going to try to do is turn this into a single fraction, a single expression, not with an addition and subtraction in between the two terms. So that means I'm going to need to find a common denominator. So 1 becomes 1 over 1. And then I'm going to multiply by x plus 2 over x plus 2 to make it the same kind of fraction as the other one. Sometimes the equation editor does not know what I'm asking it to do. The second term here already has that denominator, so I don't need to do anything with it. Now, when I multiply 1 over 1 by x plus 2 over x plus 2, I'm still getting the equivalent of 1, but I'm writing it as x plus 2 over x plus 2. And then I'm going to subtract the second term. When I combine these into a single fraction, I'm going to subtract in the numerator. So this will become x plus 2 minus x over the common denominator, x plus 2. And then my x's here are going to cancel x and minus x. And that's going to leave me with 2 over x plus 2. Okay, great. So now we're going to do the same thing for the denominator, the expression in the denominator. So I need to find a common denominator. And so that's going to be times x over x plus 1 over x. If I multiply 1 over 1 by x over x, I just get x over x. And I'm being careful about this because if your constant isn't a 1, you're not just going to get x over x. You are going to have to multiply in the numerator. And now that I have common denominators, I can add my numerators together, and I get this expression. So my originally complex fraction is still complex, but I've simplified it a little bit in that I now have a single fraction. Instead of 2 expressions, I have 1 fraction in the numerator, and I have 1 fraction in the denominator. And as I said, this middle bar here is just division. So what I'm really doing is I am taking this fraction and I am dividing it where's my division symbol? There it is. By the 1 in the denominator. Now, what do we do when we do division with fractions? Well, we're going to end up multiplying by the reciprocal. So instead of dividing by x plus 1 over x, we're going to multiply by x over x plus 1. And what do we do when we multiply? We just take our numerators and we multiply them, and then we take our denominators and we also multiply them, and we're done. We can't simplify anymore. If I distribute, I'm just going to get a quadratic, and I can't cancel a quadratic with the 2x unless I can factor out a 2 or I can factor out an x. And given the expression that I have here, I can't factor a 2 or an x out of what I have right now. It's not going to change anything if I FOIL. So remember that you can't just even if you got a 2x in the middle, you can't cancel it. When you can only cancel when you're multiplying and dividing, not when you're adding and dividing or adding and multiplying. All right, so that's method 1. Now, again, we should get the same answer regardless of which strategy we employ here. So let's go back to our original problem. And again, I'll recopy it. Now, in this case, our common denominator for all of the fractions in the expression is x times x plus 2. I have a denominator of x in the denominator, and I have a denominator of x plus 2 in the numerator. That's all it is. So I'm going to multiply both the numerator by x times x plus 2 and the denominator by x times x plus 2. So essentially, what we've got here is this expression, and we're going to multiply times x plus 2 divided by x times x plus 2. Now, this means that I'm going to distribute the x and x plus 2 through both the numerator and the denominator. So in the numerator, when I distribute this, I'm going to get 1 times x plus 2 minus x times x plus 2 divided by x plus 2, which was already there. And then in the denominator, I'm going to do the same thing. 1 times x plus 2 plus 1 over x plus 2 over x, because 1 times x, etc., is just itself. Now, what can I simplify? So in this fraction portion of the numerator, what I can cancel is the x plus 2 and the x plus 2. And in the denominator, I can cancel the x and the x. So what is this going to become? Well, it's going to still be a fraction, but I'm going to have x times x plus 2 minus x times x. And then in the denominator, I'm going to have x times x plus 2 plus x plus 2. Now, I have to do some distributing so that I can simplify. I could try factoring in place, taking out a common x, taking out a common x plus 2 in the denominator, but I don't have to do that. I can just, sort of brute force it instead of being elegant and fancy. So if I distribute, I get x squared plus 2x minus x squared. My x squareds are going to cancel in the numerator. And in the denominator, I'm going to get x squared plus 2x plus x plus 2. I'm going to be able to combine like terms. In the numerator, I'm going to get 2x. And in the denominator, I'm going to get x squared plus 3x plus 2. And if you check, you'll be able to see that this does indeed factor as x plus 2 times x plus 1. So even though these processes are a little different, you do end up with the same answer. They're algebraically equivalent. Here, again, it was a little easier to just distribute and then refactor, but I could have seen that I have a common x plus 2 here, factor out the x plus 2, and then I would have been left with an x and another 1 copy. So x plus 1 would be my second factor. And here I could have factored out an x, and then I would have been left with x plus 2 minus x, and I still would have gotten the 2x. So again, regardless of the strategy you choose, you're going to end up with the same solution.